Okay guys, in this video lesson we're going to take this idea of thermal conduction and we're going to take a look at the result of that now, okay? So as we warm things up, right, as things get hotter, they will expand, plain and simple, okay? So pretty much everything in our universe, as you warm it up, it gets larger, okay? It expands three-dimensionally, expands left, right, up, down, every direction, okay, in terms of expansion. Now, as things get colder, they contract or they get smaller, okay? And let's take a look at how that is and why that is, right? So first of all, thermal expansion, result of heat transfer or a warming effect. Here's what happens. When you increase the kinetic energy of the particles, they vibrate, and they vibrate more violently. With that more violent vibration, that takes up more space, okay? Now, if you are going to cool something, the opposite effect happens. So this would be before you heat something or after you cooled it down, the particles vibrate and they stay tightly packed. Now, as you warm them up, or if you heat this substance up, those vibrations come greater and that makes things spread out. So things expand, okay? We're going to jump out here to this little animation to see it in a little bit more detail. So here we have cool matter, it's held together by intermolecular forces, and then as you warm it up, it actually vibrates more. So you actually see it take up a little bit more space than this one is. Now, what happens is when you look at things, let's say in construction or building, those kind of things. Okay? Have you ever driven over a bridge in Minnesota and noticed there's kind of like a thump thump as you go over a bridge, or even in the middle of the bridge? You might have even seen teeth like this if you look closely at the beginning of a bridge or sometimes multiple spots along the bridge. The reason why they're there, if you take a look at it, is because of thermal expansion. In the state of Minnesota, we can get down to negative, 20 degrees Fahrenheit here and up to over 100 degrees Fahrenheit. So that's a huge range of temperatures, which means that's a huge range of thermal expansion and contraction. So our bridges, our roads, our railroad tracks, our buildings, our sidewalks, everything that we build has to allow for the thing to get bigger and smaller through our seasons. The way we do it on our roads is we build in what's called expansion joints, especially on our bridges, which have a lot of concrete in them. So this joint runs the whole length of the bridge. It's actually a separator in the actual bridge. And they calculate, using the correct physics formulas, the type of material they have, they calculate how small is possible that the bridge will get. And they make sure that they set these teeth so they'll never get past basically this point here where they're wide out. Then they go in and they calculate how long it can get or how big the bridge can get. And they make sure the teeth goes deep enough so these can slide into each other. So if you would come back, this is definitely a wintertime picture. If you'd come back in this picture and see this in the middle of summer when it's super hot out, these teeth would have actually slid all the way in and they would join perfectly with each other. Okay, that's how much our bridges expand and contract through the seasons in here. They do the same thing for railroad tracks. They do the same thing for all those kind of things to deal with that thermal expansion. Now, here is how it works. Okay, we're going to look at just the length down a bar. Keep in mind it would also expand by width, but we're going to focus just on the length right now. Okay, so the first thing that it depends on is how much material is there. So the original length, or LO, is part of our math. Okay, so here's your original length of your material, and then if we are going to warm this, okay, as we warm it, what happens is the material will expand and it'll get longer. Okay, and we'll actually see this in class. Okay, so there's an additional length that gets added, not because we're actually adding a piece on, but the particles inside of here just stretch out. Okay, and that length is our change in L. Okay, so we have our original length and our change in length. If we take a look at the actual equation that comes from putting these two things together, we say that the change in length that we get will equal, this is the Greek letter alpha, okay, this is our original length, and this is our change in temperature now. Okay, capital T for temperature, not for time here in this case. All right. So looking at our equation, our change, our original, temperature, and this alpha, it's the multiplier because whatever this substance is made of, it has its own coefficient of thermal expansion. All right. So if this was copper versus aluminum versus iron versus wood versus plastic versus concrete, whatever that material is, it has its own unique coefficient of thermal expansion because every substance is a little bit different. Okay, so this is where we factor that in. Everything else is universal. This is our big thing that's new for us here. Okay, From this, as long as we know how big it was to start, how hot we got it, we can figure out how much it grew, okay? Or vice versa. If it cools down, we can figure out how much it shrinks, all right? Now, let's take a look at something like this donut hole here, all right? So if this was a ring, let's say, of copper, okay? If we heat this up, will the inside hole get bigger or smaller? Okay? So take a second, think about that in terms of what we've been talking about. What's going to happen? Will the inside hole get bigger or smaller? Okay? Once you've decided your answer, okay, go ahead and pause the video maybe, and then decide, and then hit play, and we'll get to the answer. Okay, so here we go. If we think about this, the easiest way to actually visualize it, if you split this into 4 equal pieces, and we let those pieces go away from each other. Now, if we were to warm each of those individual pieces up and make them expand, they would all get bigger, they would get longer, and they get wider. So all that would happen. And then if we put those pieces back together, okay, now we take a look at the result of this. So what has happened to our circle, all right? Here's our original circle that they just outlined. It's this light green here. Our new one is a dark green. So the hole on the inside actually gets bigger, okay? A lot of students often think that the hole on the inside will get smaller because they think everything's going to expand. But remember, it expands in all directions. So because it expands in all directions, okay, the hole actually ends up getting bigger in this case versus getting smaller, okay? Now, other things we can apply to this, well, if you have a lid that's stuck on a jar, run hot water over it because it's going to make everything expand. Okay? Again, the hole gets bigger, so the lid itself is going to get bigger, which is going to loosen up that jar. Okay? Also, if there's something sticky on the inside of that that's causing it to, you warm it up, and sometimes it makes it less sticky in there too. Okay? Now, we also have things called bimetallic strips, and bimetallic strips, the way they work is there are 2 metals that are welded together on a strip. Okay? And if you imagine, each of these metals has a different coefficient of thermal expansion, all right? If we were to heat this up, and each of these metals has a different coefficient of expansion, because they can't slide past each other, what happens is they cause a bend, okay? This process actually was used in thermostats for the longest time, okay? So let's see what happens here. Now, if we heat this, we're seeing that we can actually get this thing to bend the other direction. As we heat this, both of these metals are going to expand. We have we'll call this our red metal, we'll call this our gray metal, okay? So the red metal is expanding. The gray metal is also expanding. What's happening though is the material is bending towards the heat, okay? It's bending towards it, which means that somehow the gray material on the outside is forcing this down and the red has to bend with it, okay? So the only way that would happen is if the gray material was getting longer, okay? So the gray material is getting longer than the red is, which means its thermal expansion is greater, okay? So if you heat this up and you bend towards the red metal, that means the metal on the outside has a greater thermal expansion, which means the metal on the inside has a less. So the coefficient of expansion for the red would be a smaller number than the coefficient expansion for the gray, okay? Let's flip it. Let's say we cool this thing down now, okay? If we cool this, take the flame away, it won't let me do that, but if I take the flame away, now the thermal contraction of the gray will be greater than the thermal contraction of the red. So the opposite effect still happens, okay? So it's going to shrink more, and if it shrinks more, it's going to bend back up towards the gray metal, okay? So another way of looking at it is you're going to get more expansion and contraction if you have a higher coefficient of thermal expansion. So in a bimetallic strip like this, when you cool it, it's going to bend towards the metal with a higher numerical value of thermal expansion. And you heat it, it's going to bend towards the one with a lower one. Okay? So they use this, or they used to use this, not so much anymore, now we use more digital. But old thermometers or in your houses that had a dial on them, you may still have one like in grandma's house and that kind of stuff, or a cabin might have these still. There's actually a bimetallic strip inside there, okay? And what they would do is that strip would actually bend back and forth depending on how warm or cold it was in the house. And it would move just ever so slightly, but they made contact points there. So if it bent just enough, it would actually make contact with another metal and it would complete the circuit. And when it completed the circuit, it would turn the furnace on. Once it got warm enough, it would bend away and it would break the circuit. So it's almost like it was an automatic switch based off of temperature that they would use. And these things were around forever. We use more digital ones now because we want to control like when you're gone and when you're home and that kind of stuff. But these things still exist. And if you just want to set it to, hey, I always want it 70 degrees in my house all the time, you could use something like this and it'll work just perfectly fine. Here is a little video on the thermal expansion of aluminum. We'll let you guys watch this. So what's going on here is this kind of, he didn't explain it very well, but he's heating up this aluminum bar, which is causing it to expand. So what's happening is that the other end is rigid. This end can slide through this little opening. So it's slowly pushing this piece forward. Now there's a pivot point here, okay? So when this pushes forward, it has a pivot point really close, which means your lever system that we have here, okay, your effort force is here, your resistance is up here, okay. Here's your pivot outside of here. So this third class lever, we're using this idea of expanding distance. So small movements here cause a big movement here, and that's on a slide, which causes this thing to move a lot here. It's called an amplifier. So you can get little distances here to visually show things bigger, okay? So this thing's probably moved a millimeter or two at the most, and it's showing that on our on our thing here, okay? That's all it does. I mean, we can turn this thing and let it run further and further and further, but then at the end of the day, all it does is go all the way up into there, and that is it. You can see how this is definitely longer here. So we go from this point to this point, and if I back the video up, you can see it's not super obvious, but you look here, this is definitely shorter than it was we get way out here. So it is definitely longer now past this point. So you can see that even visually here. It's enough that you can visually see it, okay? And we'll do this in class for you guys to see it also. Now, this example is a little bit more dramatic, okay? Once in a while in Minnesota, roads will actually heave because they expand too much and they can't go anywhere. So they actually will buckle up, and that actually will create kind of a road danger in the road. Usually when that happens, they put cones out and block the lane, and they fix it as fast as possible. In this case, they didn't quite get it fixed fast enough. So there's the buckle, as you can see in the road. And that comes from thermal expansion. It's not because water, it's not because something underneath it. Literally the road tried to expand, and this is the point that must have been weakest. And it just couldn't go anywhere, so it popped up instead. So here we go. Yep, that was a pretty legit jump. I want to see that one more time. And look at that airtime he got. Wow.